Hello ladies and gentlemen, we're going to do some function composition practice and we're going to talk about the domains of these composite functions. So there's some tricky stuff going on here. First thing we're going to do is just get the composite functions. So I want f of g and I want g of f. So for f of g, another way to write that is f of g of x. And what that means is we're going to take g of x as our input and we're going to plug it in to f. Everywhere we see an x, we're going to put the whole function g. So we'll now have, if we think about like what f of x looks like, 1 over its x minus 3. But instead of writing x, I'm going to write the whole function g of x, which is x squared plus 1. Now I'm going to simplify that, and I'll use their notation. That would be 1 over x squared, and then plus 1 minus 3 is minus 2. So I have my function. We'll talk about the domains in a second. Let's also do g of f of x. So g of f of x in the other notation looks like this, g of f. And what that means is we're taking f of x as our input and we're going to plug it in everywhere we see an x in function g. So instead of x squared plus 1, we're going to write something squared plus 1. And in this case, the something, the function that we're plugging in, is f. So 1 over x minus 3. I'm not going to simplify that. I'm just going to leave it alone. You could write that as g of f like this. That's how they wrote it. So either way, both notations you need to be familiar with. You're going to see both. So now that I have the functions, let's talk about finding the domain. This is really the weird, tricky thing in this. So when you're trying to find the domain, you need to first check to see if your input function has any domain or restrictions. So g of x, if you look at g of x, you need to say, does this function have any domain restrictions before I even look at the new function. G of x is a parabola. It doesn't have a denominator with a variable in it. It doesn't have a radical in it. So this is the domain of this function is all real numbers. We don't need to worry about it. It goes from negative infinity to positive infinity. So the first check is, does the input function have any domain restrictions? And the answer is no, it doesn't. But you also need to check the new composite function for any domain restrictions. So since this has a variable in the denominator, I know that x squared minus 2 can't be 0, because then we would be dividing by 0. And probably the easiest way to solve this would be, since it's not factorable, add 2 to both sides and then square root. But what you have to remember is when you square root, it's plus or minus. So every time you square root both sides, you need to remember to put a plus or minus. There's two answers to this: positive radical 2 squared or negative radical 2 squared, both equal 2. So on our number line, the way I would draw that for our domain would be, I'm going to put dots at negative radical 2 and positive radical 2. And since these are discontinuities, we're going to put open circles. You can't divide by 0, so you can't include those. There's no radical in here, so we can do positives and negatives. So we're going to go forever to the left, the middle, and to the right. And this is going to be our domain, which I'm going to write in interval notation. So in interval notation, that would be negative infinity to negative radical 2 with parentheses, union, negative radical 2 to radical 2, union, radical 2 to infinity. That's the domain of f of g. Now we're going to find the domain of g of f. So you look at this one, and what I said before is you first need to see, are there any domain restrictions on the input function, f of x? So are there any domain restrictions? Yes, there are. You definitely cannot plug in 3. X cannot be 3, because if you plug in 3, you get 0. So that domain restriction is coming from function f. But if we then look at our new composite function, it turns out that it didn't really simplify or change. That domain restriction is still there in the new one as well. Sometimes it is, sometimes it changes, and you end up having extra domain restrictions. But in this problem, we can just say, well, x doesn't equal 3, so on a number line, the way that would look is just an open circle at 3, and since everything else works, you can have positives and negatives. The way we would say this in interval notation would be from negative infinity to 3, union 3 to infinity. And again, that's an open circle because you can't plug in 3. That's dividing by 0. Okay, let's try another one. First thing, we're going to do f of g. So that means, again, f of g means you're taking g as the input and you're plugging it in everywhere you see an x. So instead of the square root of x minus 1, I'm going to put 1 over x minus 1. So x is now the reciprocal, 1 over x. And I'll also find g of f. There we go. That means we're taking f and we're plugging it into g. So to do that, I would have 1 over, and my input is the square root of x minus 1. These domains are going to be a lot trickier. So we're going to have to go through this pretty thoroughly. This is rough. First thing, for f of g, you need to look to see if there are any domain restrictions on the input function, g of x, and there are. Since g of x is a rational function, there's a variable in the denominator, we know that x cannot be 0. X can't be 0 because then you would have to divide by 0 on your input function and you wouldn't be able to use any output to plug into f. But we also have to look at our new function that we created and see if that has any domain restrictions. And it does because you have a radical. Now you can see x definitely can't be 0 in this, but you also have to remember that the part underneath the square root has to be non-negative, has to be greater than or equal to 0. So this is a nonlinear inequality, which means I need to make a sign chart. So I'm going to first think about where my zeros would be for this function, and the zeros would be at positive 1. If you have 1 divided by 1, you get 1, and 1 minus 1 is 0. So I know that if I plug in 1, I will get 0, and that's going to be on my number line. But now what I need to do is also include 0 on my number line, which is an open circle, because you definitely can't divide by 0 either. So we got those 2 points on our number line, and we're going to make a sign chart and figure out where this thing's positive. So maybe I can stretch this guy out. Make this thing bigger. There we go. Nice. All right, we're going to make a sign chart for this function, and we're going to figure out what happens to the left, in the middle, and to the right of those critical points. So if we pick a negative number, 1 divided by a negative number, so let's say like 1 divided by negative 1. That'd be a negative, and a negative minus 1 more is also negative, so a negative minus a negative is a negative. You would get a negative number if you plugged in a negative. Why can't I make that? That's better. How about a decimal, like 0.5? This is tricky. 1 divided by 1/2 is actually 2 because it's copy, change, flip. So 1 divided by 1/2, there's 2 halves in one whole. You're going to end up with a number that is bigger than 1, and then you're going to subtract 1, which will always be positive. So for your sign chart, the decimals are actually going to be nice because 1 divided by a decimal is always bigger than 1. And then pick a number bigger than 1, like 5. 1/5 minus 1 whole is going to be smaller than 1, so that's negative. So if it says where is this function greater than or equal to 0, that happens right here on the positive interval. So the domain, we know that x can't be 0, but we can say that the domain is between 0 and 1. 0 has parentheses and 1 has a bracket. And that's about as hard as they get for what we're doing. Because you have to make a sign chart for not even something that's easy to graph. You could graph this and look at it that way and figure out where it's positive, but I did it with sign chart. So let's go now for g of f. So first thing, let's look at the domain restrictions for f, because that's the input function. You got to say x minus 1 has to be greater than or equal to 0, which means you got to pick numbers bigger than 1. If you try and pick a number smaller than 1, you break it in your input function, and then you can't use that to plug into the output function, or the composite function. So we know we got to pick numbers bigger than 1, and then we're going to look at our new composite function and see if we can add to that. And it looks like we're going to have to say x minus 1, the square root can't be 0, which means x minus 1 can't be 0, which means x can't actually be 1. Because if you did plug in 1, you would get 0, and the square root of 0 is fine, but the square root of 0 is not fine in the denominator. So we're actually going to pick all the numbers that are greater than or equal to 1, but then we're going to toss 1 out. So we're just going to say, actually, no, not all of them, the ones that are strictly greater than 1. Since the radical is in the denominator in your composite function, you have to kick 1 out, because 1 would mean you would be dividing by 0. So it's just going to be from 1 to infinity in interval notation, 1 to infinity, and those are both parentheses. All right, so last problems, I guess, there's 2 of them. we're going to do the same thing. So we'll find f of g. And f of g, that means we're going to plug g into f. So instead of the square root of x plus 1, it's going to be the square root of x squared plus 2x. And then we got to throw on the plus 1. So I put x squared plus 2x in for x. Let's see. That's a factorable polynomial, and it's actually a perfect square. So if you factor the denominator, or not the denominator, the radicand, if you factor the radicand, you can see that this is x plus 1 quantity squared, which if you square a square root, you actually just get that part underneath, f of x, or f of g, I should say, f of g, is x plus 1. There's some trickiness going on here. This is only going to work, like you're never going to get a negative number since something is being squared. So this actually, like from a real technical standpoint, is the absolute value of x plus 1. Don't want to get too hung up on that, but what I'm mainly concerned with is, can you create the composite function? We're going to skip the domain for this one because I just don't want to get too hung up on it. Let's talk about this one, g of f. So g of f, we're going to do something similar. We're going to take f and we're going to plug it into g. So it'll be something squared plus 2x, and in this problem that would be the square root of x plus 1. Oh, I should have wrote x. Something squared plus 2 times, I'm not writing x, I'm writing the square root of x plus 1. Okay. So the square root of x plus 1 squared plus 2 times the square root of 1. This is also really messy. Let's find the domain of that one. So we're going to first look at the domain of the input, which actually is going to show up here as well, so it's going to be the same. We're going to say that x plus 1 has to be greater than or equal to 0, which means x has to be greater than or equal to negative 1. The way we would write that and draw it on the number line is we would say from negative 1, and we're going to put a closed circle. So closed circle at negative 1, and we want the numbers bigger than negative 1, so that would go to the right. So that would be in interval notation, negative 1 to infinity, and negative 1 has a bracket. So that's finding domain of composite functions. That is definitely a tricky thing to do. So I would encourage you to go back, take a look at the other problems that we did, make sure you feel pretty good about those. Then you can work on your unit review quiz and your math labs and all that stuff. So good luck, and be sure to hit that like and subscribe button.